Hi folks, today we're going to talk about solving exponential equations and log equations. So I have a couple different examples to go through. We'll start with some exponential equations. And here's the idea behind solving exponential equations. If you have an exponential equation, that means your variable is in the exponent. And so in general terms, we say, well, if base b raised to the m power is equal to base b raised to the n power, that's an m and an n, then it has to be true that m and n are equal to each other. So let me show you a really quick example here. If I have 2 to the x is equal to 2 to the third, it must be that x is equal to 3. So our goal whenever we are solving exponential equations is to get those bases to be the same. And if we can get those bases to be the same, then all we have to do is set those exponents equal to each other. So we'll go through a few examples. We're going to try a few examples that are a little bit more involved than something like this. So let's say, for example, we have 2 to the 3x minus 8 is equal to 16. Now, right now, clearly our bases are not the same. And in order to solve for x, we need to get those bases to be the same. The common mistake that people make is that they alter one side of the equation, which then gives them a situation where they no longer have equality on either side. You do not want to change the value of anything in your equation. All you want to do is rewrite it in a different way so that the value doesn't change. Okay, so it's a common mistake that people make. And what I mean by that is this. I can actually rewrite 16 as base 2. It's the same as saying 2 to the 4th power. So notice I didn't change the value of anything. All I did was rewrite the right side of my equation so that it has the same base as the side on the left. Just write that so it looks a little better. There we go. And so now all I need to do is set my exponents equal to each other. So 3x minus 8 is equal to 4. And then it becomes a very easy problem to solve. We end up with x is equal to 4. Okay, so that's the idea behind these. Now, sometimes you only have to change one side of your equation. Sometimes you'll have to change both sides of your equation. But as long as you remember to not change the value of anything, then you'll be fine. So let's do a couple of other examples, and I'll explain to you what I mean by that. If I have the problem 27 to the x plus 3 is equal to 9 to the x minus 1. And so our inclination might be, oh wait, 9 goes into 27. Sure, it does. But that's not going to help us because I can't raise 9 to any power to get 27. So some people think, well, I'll just multiply this side by 2, or I'll just divide this side by 3, or sorry, multiply this side by 3 or divide this side by 3. Which you would think would work, but it doesn't, because remember, order of operations, I can't divide this by 3 because of that, because of the exponent. Okay, so what I can do is rewrite both sides so they have a common base. I can break them down to their most basic form and recognize that 9 can be broken down into base 3, and as can 27. I can rewrite 9 as 3 squared, and I can rewrite 27 as 3 cubed. So again, I haven't changed the equality of anything. All I've done is changed how I'm writing 27. And so I still have x plus 3 here, and here I still have x minus 1. And if you remember back probably a couple years ago when you did problems like this where you're raising an exponent to a power, you are just multiplying those together. So when you do multiply them together, we end up with 3 to the 3x plus 9 is equal to 3 to the 2x minus 2. Okay, make sure you distribute that to both terms up there. And now, again, because I have a common base, I can just set my exponents equal to each other. 3x plus 9 is equal to 2x minus 2. And when I solve that, I end up with x equals negative 11. Okay, so that is the basic way of solving exponential equations when you can get their bases to be the same. However, we do have situations where we can't do that. We can't get the bases to be the same. For example, if I have 6 to the x is equal to 11. Okay, for example. Clearly, I cannot get those bases to be the same. And so when you have a situation like that, we need to take the log of both sides of the equation. Okay, we need to take the log of both sides. So just like you do with anything else, like you can multiply both sides of the equation by something, divide, square both sides, take the square root of both sides, you can also take the log of both sides. So if I take the log of both sides, I'm saying the log of 6 to the x is equal to the log of 11. And now if I use my property, if I use my power rule, I can bring that out in front. So that gives me x log of 6 is equal to the log of 11. And then I can divide both sides by log of 6. Divide by the log of 6. Now let me show you something here. When you're doing this on your calculator, you want to make sure that you use the log button properly. Clear that out. So if I'm doing this, I'm saying, okay, log of 11. Make sure that you close your parentheses right there, because if you don't, you're going to get the wrong answer. Divided by the log of 6. And that gives me x is equal to 1.34 roughly. 1.34. Okay, roughly. Now let me show you something else. If I instead of say logging both sides, if I took the natural log of both sides, so let's say I did ln of 6 to the x is equal to ln of 11. Right, I still use the same rules. Remember, ln is just log base e. And so then I end up with x is equal to ln of 11 over ln of 6. Okay, if I did that in my calculator, so I've got ln of 11, close your parentheses, divided by ln of 6, close your parentheses. Notice you get the exact same answer. Okay, you get the exact same thing. Let me pull up the calculator again so you can see that. Okay, so you get the same thing. So you can log both sides or ln both sides. So take log base 10 or take the natural log of both sides. Okay, so that's the idea behind that type of equation when you're solving exponential functions where you can't get the bases to be the same. Now, let's do another example of this that's a little bit more complex. And I only want to show this to you because of the fact that it's easy to make careless mistakes with a problem like this. So let's say, for example, we have 5 to the x minus 2 is equal to 4 to the 2x plus 3. Clearly, right, I can't rewrite either of those to get the bases to be the same. So I'm going to take the log of both sides. I'll do ln this time. So I have ln of 5 to the x minus 2 is equal to ln of 4 to the 2x plus 3. Okay. Now, properties say that I can move this entire exponent out in front. You have to make sure that you use parentheses here, because if you don't, then you're not following order of operations. So make sure if that exponent has more than one term in it that you use parentheses. Okay, so I have ln of 4. From here then you're going to want to distribute, because remember we have to solve for x. We have to get all of our x terms on one side of our equation. So I have x ln of 5 minus 2 ln of 5 is equal to 2x ln of 4 plus 3 ln of 4. So all I did was distribute. Now I'm going to take all of my x terms and put them on one side of my equation and move everything else to the other side. So I have x ln of 5 minus 2x ln of 4 is equal to 3 ln of 4 plus 2 ln of 5. Okay, so I just moved this term over to this side and moved my 2x ln of 4 term over to this side. And so now here I can factor out, right? X is my common factor. So if I factor x out, I end up with x times ln of 5 minus 2 ln of 4 is equal to 3 ln of 4 plus 2 ln of 5. And then to solve for x, I'm just dividing both sides by ln of 5 minus 2 ln of 4. Okay, ln of 5 minus 2 ln of 4. And again, when you do this in your calculator, make sure that you use parentheses. So I need to put parentheses around my entire numerator. So I have 3 ln of 4. Then I need to close my parentheses around the 4, so that the calculator follows order of operations. 2 ln 5. I have to close that parenthesis around the 5, then I have to close the parenthesis around the entire numerator. Okay, then divided by parentheses. ln of 5, close my parentheses, minus 2 ln of 4, close the parentheses around the 4, and then close the parentheses around the denominator. And I end up with x is approximately negative 6.34. Okay, so that's another example of how you would go about doing a problem like that. Okay, so that's the idea behind that. I've got one more type of problem that I want to go through with you, and it has to do with when we are solving a problem where we have multiple x's in base e. So if I have e to the 2x minus 4e to the x plus 3 is equal to 0. If you treat e, right, if you treat e to the x, you could almost do this. Let e to the x equal some other variable. Let's say it's a. Then this is the same as saying a squared minus 4a plus 3. And hopefully you see that that can be factored, right? I have a minus 3 times a minus 1, which would give me a equals 3 and a equals 1. Now you can go back and substitute in. E to the x is 3, e to the x is 1. And now to solve that, just take the natural log of both sides, right? Because our variables and our exponents. So ln of e to the x is equal to ln of 3. Now this is, remember, ln is just log base e. So this is the same as saying e to what power gives me e to the x, right? So this answer over here, when you have ln of e to some power, your answer is always just that power. So x is just ln of 3. And that's an exact value, so you can leave it exactly like that. Okay? Over here we get e to the x is equal to 1. Well, then the only thing that x can be there is 0. So your solutions are x equals 0 and x equals ln of 3. If they ask you for an exact answer, you can just leave it. If they ask you for an approximation, then you can do that in your calculator. The approximation of ln of 3 is like 1.10. So that's it for now. That's how you go about solving those problems. Good luck with the assignment, everybody. Take care. Bye-bye.